Engineering failures often stem from internal stress that remains invisible until the structure fractures. Software environments face a similar risk. Adding complex monitoring tools to a production system can create the very instability they are designed to detect. This creates a persistent tension. Administrators need to see the internal state of a CMS to troubleshoot it, but every diagnostic hook becomes a potential new entry point for an attacker. When diagnostic tools are tightly coupled with the host application, they can introduce fatal errors, memory leaks, and hard dependencies that compromise the entire environment. To understand the solution, we have to look at the standard web server stack. An incoming browser request passes through the web server, hits PHP FPM and the XOOPS score, and finally queries a MySQL database. XOOPS DebugBar 1.3 addresses the risks of the stack by employing a strict, capability-based observer pattern. This architecture extracts deep diagnostic metrics without ever modifying the host application's core runtime logic. We will now map the PHP request lifecycle to examine how data is collected, programmatically sanitized, and persisted. The goal is to build a system that observes every detail of production behavior while remaining entirely fail-safe. This timeline diagram represents the request lifecycle. The entry point, labeled core.include.common.start, triggers as soon as a request enters the environment. In this early phase, the module attempts to register its autoloader and attach loggers to external packages like Monolog, Ray, and Tracy. This is governed by a strict mandate. The core XOOPS application must never become dependent on an optional diagnostic package. Rather than relying on hard imports, the module uses explicit runtime checks, evaluating class exists and function exists before attempting to execute any integration logic. If a third-party package is detected and valid, the pathway opens and the logger attaches. If a package is absent, the integration degrades silently. The request continues without throwing an error. This design prevents system crashes during deployment drift, such as when development tools are removed from a production server. Even the module's own core capabilities must pass these checks before the toolbar is permitted to initialize later in the cycle. By treating every integration as optional and untrusted at boot, the architecture ensures that diagnostic failures cannot cascade into application failures. As the request execution moves forward, we reach the mid-request nodes where the CMS generates runtime data. The observer intercepts these data streams, focusing specifically on SQL logs, block caching states, and template variables. All intercepted data passes through the diagnostic sanitizer. Here, the packets are broken apart into structural metadata and raw payload values. The sanitizer performs a recursive redaction of sensitive keys, stripping session IDs, authorization headers, and CSRF tokens from the diagnostic record. It then bounds array depth and limits string lengths to prevent the diagnostic interface from causing memory exhaustion. This filtering ensures that even an exposed debug view cannot leak user passwords or crash the server. One of the most sensitive diagnostic vectors in this lifecycle is dynamic SQL explain analysis. Allowing an administrator to arbitrarily execute explain on production queries is a security risk that requires specific mitigation. In version 1.3.0, an inbound explain request must be matched against a dedicated HMAX signing key before it is authorized for execution. This signing key is stored in a protected data directory, physically isolated from the web root and inaccessible through standard browser requests. Once authorized, the request passes to a validation parser that ensures the input contains only a single statement. The parser enforces strict constraints. The query must be a read-only select or a common table expression where the top-level command is select. Stacked statements are rejected. Security in observability assumes that every diagnostic payload is a potential leak, requiring logical isolation before any value is rendered. This diagram shows the end of the request lifecycle at the core.footer.end termination event. At this stage, the system finalizes the request profile and splits the collected metrics into two streams. The first stream provides the data for the immediate browser toolbar, allowing for single request profiling. The second stream is compressed into a single compact row within the DebugBar profiles database table. The table intentionally excludes full post data and raw SQL results, storing only small numerical summaries and bounded identifiers to keep the storage footprint minimal. The system enforces storage budgets by capping the table at 10,000 rows and purging records after a rolling 7-day period. Single-page profiling is useful, but systemic performance issues often only become visible when looking at aggregate data. By compiling this data, the system can generate systemic N+1 query leaderboards, track OP cache health, and identify bootstrap time violations. Shifting from single request isolation to aggregate analytics allows developers to locate systemic bottlenecks without introducing database overhead that could destabilize the host. This macro-level view shows the complete secured lifecycle. The main application flow remains undisturbed, while the observability layer safely extracts data at key nodes. Throughout this process, the debug bar acts exclusively as an observer. It never participates in the core application logic. Effective performance tracking relies on empirical data collected within these strictly defined limits. For developers extending this module, these architectural rules are mandatory. You must use the established public instrumentation API rather than creating secondary, unverified data paths. All custom integrations must enforce capability checks and respect the boundaries of the diagnostic sanitizer to maintain the integrity of the host application. This architecture provides the detailed evidence needed to solve production issues without introducing new vulnerabilities to the host application.